Okay, so good morning everyone. So in today's lecture, I am going to continue my discussion on isoperimetric problems. Okay, so let us just recall the major result that we derived in the last lecture. What we derived was if we have to extremize a functional j subject to the constraint g, which is an isoperimetric constraint. So, well, let me denote it by I, which was an isoperimetric constraint. So, this is my isoperimetric constraint. Then the result is the necessary condition for the extremal. The necessary condition for the extremal was the satisfaction of the following ODE, right. So j was integral f dx. So what we have is the following. Well, let me call this as capital F minus partial f partial y is equal to 0, where my capital F was f minus lambda g, where lambda is a constant which is a real number. Okay. So let us now look at let us continue our discussion for the class of these set of problems, and let us look at some examples where we impose isoperimetric constraints. So my first example this morning is we are going to revisit our catenary example, the problem of catenary, or finding the optimal shape of the cable subject to some constraint on its weight or on its potential energy. So we have to extremize the functional which was given by integral from x0 to x1 y of square root 1 plus y prime square dx subject to the length constraint given by I of y is equal to integral from x0 to x1 square root 1 plus y prime square dx, which is given to be a fixed number, let us say that is equal to L. So this is the isoperimetric constraint that we have. So then let us now, to find the extremal, let us assume, although this assumption is not necessary in the general case, but we are trying to simplify the problem. Let us assume without loss of generality that my x0 is 0 and my x1 is 1. So my total domain length along the x axis is 1, right. So and further we assume that the height of the poles are also fixed, right. So poles that is the same height is also fixed, right, and this is positive. So which means, so given these set of assumptions, it means that my fixed boundary conditions are y of 0 is equal to y of 1 is equal to h, right. So what I have is the following. Further we also assume that the length of the cable here is greater than 1, because if L is equal to 1, then the only solution that is possible is a straight line which is parallel to the x axis, and if L is less than 1, then there won't be any solution. It is quite intuitive to see that, right. Okay, so then we are going to directly use this result above. So let me call this as star. So, we are going to use this result star to find the extremal. So, using star, I see that my y, which is the extremal, is a solution to star, right, and in that case I get that. So, I get that it must be the solution to star, and notice with my capital F being the following. It is f minus lambda g, which is also equal to y times square root 1 plus y prime square minus lambda times square root 1 plus y prime square, right. Notice that this quantity is independent of the variable x, or the independent variable, right. So, it is independent of x explicitly. So, which means we can very well use the Beltrami identity. We can use the Beltrami identity, which says that h given by y prime f of y prime minus f, where the subscript y prime denotes the derivative of capital F with respect to y prime, the partial derivative. This is set equal to a constant. Okay. Let me call this as C0. So, then when we plug in the value of f, which is this quantity, after simplifying I get the following equation: y minus lambda is divided by square root 1 plus y prime square times y prime square minus y minus lambda square root 1 plus y prime square is equal to a constant C0, right. So, from here I can simplify this result a little bit further in order to finally integrate y with respect to x. So, I see that after simplification, so let me call this as my result double star. So, simplify my double star and integrate with respect to x. I see that this is also, after doing all the steps, let me write down the result. So, y comes out to be the following. So, y of x is lambda times lambda plus C1 cos hyperbolic of x minus C2 by C1. So, that is my extremal, this time the extremal with the Lagrange constraint lambda. So, now the next set of steps is to look at this solution and see what are the plausible values of C1 and C2. So, to do that I am going to change my set of constants. So, I am going to introduce new set of constants, my kappa 1 to be C1 and my kappa 2 to be minus C2 by C1, the new set of constants, and I see that with this set of constants I use my boundary condition. So, use y0 of h is equal to y1, this is also equal to h. From here what I see is I get two sets of equation, h minus lambda using the value y0 is equal to C1 times cos hyperbolic of minus C2 by C1, which is kappa 2, right, and C1 is kappa 1, and using y1 I get this is also equal to kappa 1 cos hyperbolic 1 by kappa 1 plus kappa 2, right. So, what we have are two sets of equations for three unknowns kappa 1, kappa 2 and lambda, and of course, we have the isoperimetric constraint, that is an completely fully determined system. And so, to find out some of these unknowns, let us see that we have this one relation using the relation kappa cos hyperbolic kappa 2 is equal to this right hand side. I get that. So, using this equality I see that my kappa 2 comes out to be minus 1 by 2 kappa 1, right. minus 1 by 2 kappa 1. Kappa 2 is minus 1 by 2 kappa 1. Okay. So, then what do we have? Then we have, well, so we have found one constant in terms of other, and we can further use the isoperimetric constraint. So, using the isoperimetric constraint, I see that L, the integral is from 0 to 1 square root of 1 plus y prime square dx, and this is after plugging in the value of y prime, take the derivative, and we see that this is also equal to integral from 0 to 1 cos hyperbolic of x by kappa 1 plus kappa 2 dx, right. And we see that this is also equal to 2 kappa 1 sin hyperbolic 1 by 2 kappa 1. Okay. So, then the next set of steps are, we can, well, here we have used the fact that kappa 2 is equal to negative 1 by 2 kappa 1. So, we have used that fact to eliminate kappa 2. Okay. So, then well, so let me introduce another set of variable, introduce xi equal to 1 by 2 kappa 1. So, what we see is, from here, from this isoperimetric constraint, I have this new equation that L xi is equal to sin hyperbolic of xi. Okay. So, now we need to solve this equation for xi. Notice that this is a transcendental equation with the left hand side a polynomial and the right hand side a exponential function. And in few lectures back, we have shown that in general we will have two solutions if L is beyond a critical value, right. So, note that first of all, xi equal to 0 is a solution, right. So, let me call this equation as my 1. So, is a solution of 1, right. So, this is equal to 0 is a solution of 1. So, this means that since xi is 1 by 2 kappa 1, this means that kappa 1 goes to infinity, right. So, this means that if kappa 1 goes to infinity, then y, which was equal to lambda plus the solution lambda plus kappa 1 cos hyperbolic of x by kappa 1 plus kappa 2, right. So, this goes to lambda plus cos hyperbolic of 0, which is equal to a constant, right. So, what we get is, if I have xi equal to 0, the trivial solution, then y is a constant, right, and that constant cannot be anything else other than h, because at the boundary y is equal to h, which means that xi equal to 0 gives me the trivial solution, which is a line parallel to the x axis with y component h, right, and this is not the solution that we are looking after. So, this is the trivial case. This is the trivial case, and we are going to discard that case. So, now we know that for L greater than 1, so that is why we had assumed that L was greater than 1. So, there exists two solutions. There exists two solutions of 1, and that has been shown few lectures back, that L for L beyond a critical value, in general there exists two solutions. So, of course, we see that this is, if we have a solution, let us say xi hat, then even the negative xi hat is the solution, right, because this equation 1 is even with respect to xi, right. So, now on the so what we get is the following. So let us assume let us assume xi is one of the solutions xi hat. So, let us assume one of the solutions. So, in that case, using this condition, I see that this is also equal to 1 by 2 kappa 1, or kappa 1 is 1 by 2 xi hat, right. Now, which means that kappa 2, which is negative 1 by 2 kappa 1, as the assumption that we began with, this is also equal to xi hat, negative xi hat. Okay. So, then we use, let me call these set of conditions, well, let me call these set of conditions as my condition number A, right. So, we are going to use A to see that using this set of condition, I see that I get my constant lambda, which is h minus 1 by 2 xi hat cos hyperbolic of xi hat, right. And finally my solution y, since all of my constants kappa 1, kappa 2 and lambda has been determined. So, my solution y of x comes out to be the following. It is h plus 1 by 2 xi hat times cos hyperbolic xi hat 2x minus 1, right, minus cos hyperbolic of xi hat, right. Okay. So, notice, so since my x is between 0 and 1, notice that the largest value of this quantity. So, this quantity is for x between 0 to 1, this quantity lies between minus 1 to plus 1, right. So, this straight line lies between minus 1 to plus 1, which means that this bracketed quantity can only be less than or equal to 0, because the largest value of this term, the left hand side term, will be bounded above by this right hand side term. So, what we have is that in general y of x is less than equal to h, right. So, the result that we have is, so this means that the cable, that the shape of the cable that we are trying to find hangs down from the pole, right, which means that if we were to draw the cable where the cable is hanging from two poles of the same height, where the x coordinates are 0, 1, we expect that the cable is hanging down, right. So, the cable is hanging down. Now, further if note that if my L is very large. So, suppose my L is very long. So, for a cable extremely large, we see that the solution to this equation, this particular equation 1, will give some erroneous result. So, if L is very large, we see that from 1 I see that xi goes to infinity, or kappa 1, if xi goes to infinity, then plugging it into this solution, I see that y is less than 0, right. Okay. So, the solution xi hat goes to infinity, and that gives from here that y is less than 0, which means that this is an abnormal result, or what it is saying is that the model that we have, the model breaks down, right, or in other words, the cable lies on the ground, right. So, there is nothing in terms of potential energy which is governing the shape of the cable. So, in that case the cable will be completely lying on the ground. So, this is the case where L goes to infinity, right. So, the cable is lying on the ground. So, that completes the analysis of this example, and this is the first example with the isoperimetric constraint setup. Let us look at more examples of this similar category. The second example that I have is on DDoS problem. So, we have looked at DDoS problem on several occasions. So, now we are going to look at the same problem with a length constraint set up on the curve, right. So, the problem again says we have to determine the height of the curve. We need to determine. So, let me just draw. So, we have a curve, let us fix. So, these are my endpoints x 0 x 1, and this is the height of the curve y of x. So, we need to determine y of x such that I say, let us also say that x 0 is minus 1 and x 1 is 1, such that y of minus 1 is equal to y of 1 is equal to 0, and the perimeter of the curve, described by L greater than 2, the perimeter of the curve described by L greater than 2, and the reason we have taken L strictly greater than 2 is because if L is equal to 2, then the only length will be lying parallel to the x axis, because the length along the x axis is 2, and L less than 2 does not make sense, we will not get a curve. So, L has to be necessarily greater than 2. So, then and the area that we describe, area is enclosed by this function y of x, and the line segment from minus 1 to 1, right. So, the length of the curve that we are trying to describe is this one and this one, right. So, the total length of the curve that we have is the length which lies along the x axis plus the length which lies along above the x axis, right. So, that is what we have. So, then what? So, let us look at this problem to find the extremal. So, we have to extremize the area. So, the area is my functional j of y, integral from minus 1 to 1 y dx, subject to the length constraint, which is integral from minus 1 to 1 square root of 1 plus y prime square dx, which is the arc length, right. So, we have to, and then this is given, the total length is given to be L. So, this is fixed. So, then we have to make sure that so since we have already taken care of the fact that L is greater than 2, we have removed certain abnormal situations where the solution or the extremal is unique, or the extremal is does not exist, or we have already removed. So, note that we have already removed the abnormal case or the case with rigid extremal, right, because my total length is greater than 2. So, sum of the length will be above the x axis. So, we will get a shape with a non-zero area. Okay. So, then what we have is my y will be, the extremal y will be the solution solution to the Euler Lagrange ddx of partial y of f minus partial f partial y equal to 0, where f is y minus lambda times square root 1 plus y prime square, right. And again we can go ahead by observing that this quantity f is independent, it is independent of the variable x, it is independent of the variable x explicitly, which means we can again use the Beltrami identity. So, Beltrami identity. Okay. So what we have is we have that h of y comma y prime is going to be y prime f of y prime minus f is equal to a constant. So, that is my Beltrami identity, and after plugging in this function capital F, I see that we get the following expression: minus lambda y prime square divided by 1 plus y prime square minus y minus lambda 1 plus y prime square, right. So, this is equal to C1. So, then what we have is we could, well, the next set of steps is we simplify this expression, this equation, and then solve for y. So, when we solve for y, I get that, well, first of all let me call this as star. So, we simplify star and we get the following expression: y plus C1 square root 1 plus y prime square. After simplification, this is equal to lambda, right. And then after integrating y plus C1 divided by square root lambda square minus y plus C1 square dx, we get this is equal to x plus C2, right. So, my C1 and C2 are constants of integration. Okay. So, the next set of steps in integrating will involve a certain substitution. We can certainly substitute y plus C1 equal to lambda sin phi, and the moment we do that, this integral becomes very straightforward, and we see that this particular integration leads to x plus C2 equal to lambda cos phi, right. So, here is the equation for x and here is the equation for y. From here what we get is that the extremal is such that we have x plus C2 square plus y plus C1 square is equal to lambda square. So, this implies that the extremal lies on the circle with radius lambda. So, lambda is the radius of the circle, right. Okay. So, then we can use, well, all it remains now is to eliminate these constants C1 and C2 by using our boundary conditions that we have, right. So, using boundary conditions, I see that y of minus 1 is equal to y of 1, which is also equal to 0, and from here I immediately I can figure out that C2 is 0, right. And then what I see that well, so immediately I see that C2 is 0. Further I can use, we haven't used our isoperimetric constraint. So, if we use our isoperimetric constraint, I see that L is given by, well, just plug the solution y as a function of x into the integral to see that L is coming out to be 2 times square root C1 square plus 1 tan inverse 1 by C1, 2 times square root C1 square plus 1 tan inverse 1 by C1. Now, notice that, so since my length L is bigger than 0, what I have is, since L is bigger than 0, then I must have that C1 is also bigger than 0. Otherwise, since the sign of this expression on the right is completely governed by the tan inverse. So, and that is positive only when C is positive. Okay, so then since I have that C1 is from 0 to infinity. So, C1 is non-negative. It means that my L. So, if I plug C1 equal to 0, I get that L is going to be will be going to be pi, right. So, L is the upper bound of L is pi, and if C1 is infinity, we will see that L is equal to 2 here, that can be shown, right. So, which means that L lies between 2 and pi given these values of C1. Okay. So, further note that, so let me call this relation as double star. Note that this relation double star is monotonically decreasing with respect to C1, monotonically decreasing with respect to C1, which means that there exists a unique, since we have a monotonic function of C1, there exists a unique C1, which satisfies double star, and also the set of conditions, let me call these conditions as A, right. So, and A. So, we do not at this stage explicitly find the constant C1 except showing that C1 is unique, which lies on the circle as well as which satisfies the isoperimetric constraint, and saying that C1 can readily be found. Okay. So, we end the discussion on this problem.